There's something deeply unsettling and utterly fascinating about the way black holes refuse to play by the rules. These cosmic monsters, lurking in the darkness of space, don't just swallow light and matter. They send out signals that defy everything we think we know about physics. Mysterious bursts of energy, unexplained echoes, patterns that appear and vanish without warning. It's as if the universe is whispering secrets in a language we're only beginning to decipher. And today, we're diving headfirst into that enigma, unraveling 25 of the most baffling signals ever detected from these gravitational abysses. Signals that shouldn't exist, signals that challenge our understanding of reality itself. Imagine standing at the edge of a black hole, a place where time slows to a crawl, where gravity twists space like taffy. Now imagine hearing something, a pulse, a hum, a scream from the void. That's what astronomers are picking up, scattered across the cosmos. Some of these signals repeat like clockwork, while others flash into existence just once, leaving behind more questions than answers. They don't match any known celestial phenomena. They don't fit our models, and yet there they are, persistent, eerie, undeniable. What could possibly be causing them? Dying stars, colliding dimensions, or something even stranger. This isn't just about solving a cosmic puzzle. It's about confronting the limits of human knowledge. Every unexplained signal is a crack in the foundation of our understanding, a reminder that the universe is far weirder and far more wonderful than we ever imagined. So consider this your invitation to the greatest detective story in science. We'll sift through the evidence, examine the theories, and venture into the unknown together. By the end, you might not have all the answers, but you'll see the cosmos in a whole new light, ready to listen to what the darkness is trying to tell us. Let's begin. Long before scientists tuned into the bizarre whispers of black holes, another cosmic mystery made headlines, one that still haunts astronomers to this day. The WOW signal, captured by Ohio State University's Big Ear radio telescope in 1977, remains one of the most tantalizing enigmas in space exploration. That single burst of radio waves, lasting 72 seconds, carved its name into history with its sheer intensity, a signal so powerful that astronomer Jerry Amon scribbled, "Wow," in red ink beside the data. For decades, most assumed it was our best candidate for alien contact. But what if we've been looking in the wrong direction? New research suggests the WOW signal might not have come from distant civilizations at all, but from something far more mysterious lurking in the cosmic shadows. Some astronomers now speculate it could have been the death cry of a star being shredded by a black hole, its final moments amplified by the hole's immense gravity. Others propose an even wilder possibility, that the signal originated behind a black hole, warped and focused by gravitational lensing like light passing through a cosmic magnifying glass. Imagine a black hole bending space-time so drastically that it acts as a natural amplifier, taking a faint signal from across the universe and cranking it up to deafening levels, just long enough for us to hear it before vanishing forever. The theories don't stop there. If the WOW signal was linked to a black hole, why haven't we detected anything like it since? Was it a freak accident of cosmic geometry? A fleeting alignment of black hole, telescope, and distant signal that will never repeat? Or could it be proof that black holes occasionally fire off bursts of energy we don't yet understand? The more we study it, the stranger it gets. Even the signal's frequency, 1420 MHz, sits eerily in a range where human-made interference is rare, deepening the puzzle. One thing's certain, if black holes are capable of producing or hijacking signals like this, it rewrites what we thought we knew about their behavior. Maybe they're not just silent monsters lurking in the dark. Maybe they're broadcasters sending out distorted echoes of the universe's secrets. The WOW signal might be 47 years old, but its greatest revelations could still be ahead of us. And if we're right about its connection to black holes, the next strange signal we detect might finally crack the code. Fast radio bursts are like the universe playing a cosmic game of Morse code, blinking into existence for mere milliseconds, then vanishing without a trace. But the most puzzling ones aren't coming from empty stretches of space. They're erupting dangerously close to supermassive black holes where the laws of physics twist into knots. Take FRB 121102, the first repeating fast radio burst ever discovered. Its home, a tiny, turbulent galaxy with a supermassive black hole at its heart, spewing out energy like a raging storm. The numbers alone defy belief. This single burst, lasting less than the blink of an eye, can outshine 500 million suns. How does something that brief pack so much punch? The leading theory points to magnetars, neutron stars with magnetic fields so strong they'd rip atoms apart at close range. Picture a magnetar spinning wildly near a black hole's event horizon, its magnetic field lines snapping like overstretched rubber bands. Each snap could launch a burst of energy intense enough to cross billions of light years. But here's the catch: some of these FRBs have patterns, repeats, twists in their signals that suggest something even stranger might be warping them along the way. That's where black holes enter the equation. Their immense gravity could act like a funhouse mirror, bending and amplifying these bursts as they pass by, or even generating them outright. Then there's the jet scenario. Supermassive black holes often fire off colossal beams of plasma at near light speed. If one of these jets plows through a cloud of gas or collides with another object, the shockwaves might trigger FRBs like cosmic fireworks. But why do some repeat while others don't? Why do their frequencies sometimes drop in a telltale slide, as if something's dragging them down? It's as if black holes aren't just lurking in the background, they're actively shaping these signals, leaving fingerprints we're only starting to recognize. The more we study these bursts, the clearer it becomes. They're not just random blips, they're messages from the most extreme environments in the universe, written in a language of energy we're still learning to read. And if black holes really are the puppeteers behind some FRBs, it means they're far more than silent vacuum cleaners of the cosmos. They're dynamic, chaotic, and maybe, just maybe, sending out signals we were never meant to understand. Yet, picture a black hole with a pulse, a steady, rhythmic flicker like the beating of a cosmic heart. That's exactly what astronomers observed in JARES 1915+105. A black hole nearly 36,000 light-years away that's been emitting X-ray bursts like clockwork every 20 to 40 minutes for decades. Unlike the chaotic violence we associate with black holes, this one has an eerie regularity, as if it's breathing. The discovery shattered expectations because nothing in our models predicts this kind of stability. Black holes are supposed to be messy eaters, devouring their accretion disks in unpredictable bursts, not maintaining a celestial metronome across 20 years of observations. The secret might lie in the delicate dance between the black hole and its swirling disk of superheated gas. Most accretion disks are turbulent, with material falling inward in erratic clumps. But JARES 1915+105 seems to have found a precarious balance. Imagine a faucet dripping into a bathtub. If the water pressure is just right, each drop falls at a steady interval. Similarly, this black hole's gravity might be pulling material from its disk in precise, rhythmic waves, heating it to millions of degrees and producing those X-ray pulses like a lighthouse beam cutting through space. What's even stranger is the scale. These aren't tiny flickers. Each pulse releases as much energy as our sun does in years. Some researchers think magnetic fields play a role, twisting and snapping like rubber bands to regulate the flow of matter. Others speculate the black hole's spin is key, creating a feedback loop where too much infalling material briefly chokes the disk, only for the cycle to reset and repeat. But here's the real mystery. Why don't all black holes do this? Is JARES 1915+105 a cosmic oddity? Or are we just not listening closely enough to others? The implications are profound. If black holes can settle into these stable rhythms, it suggests they're far more than simple destroyers. They're dynamic systems with their own circulatory patterns, perhaps even influencing the growth of entire galaxies around them. And if we can decode why this particular heartbeat persists, it might reveal universal principles governing how black holes and their disks interact, principles we've barely begun to glimpse. For now, though, that steady pulse remains a tantalizing enigma, a reminder that even the darkest corners of the universe have their own unexpected cadences. V404 Cygni doesn't just devour matter, it spits fire. This black hole, lurking 8,000 light-years away, has become infamous for its violent tantrums, erupting without warning in gamma-ray flares so intense they briefly outshine entire galaxies. In 2015, astronomers watched in awe as V404 Cygni unleashed a series of these eruptions, flickering like a cosmic strobe light every few minutes. But here's what defies explanation. Gamma rays shouldn't behave this way. They're the universe's most energetic light, usually streaming from supernova or colliding neutron stars, not bursting from black holes in erratic, pulsing waves. The culprit might lie in the chaos just outside the event horizon. Picture a whirlpool of superheated gas, spinning so fast it generates magnetic fields trillions of times stronger than Earth. When these fields snap and reconnect, a process called magnetic reconnection, they can blast out jets of energy at nearly light speed. It's like cracking a cosmic whip, sending shockwaves through space. But V404 Cygni's flares don't follow the rules. They're uneven, stuttering, as if something's disrupting the black hole's feeding frenzy. Some theorists suggest clumps of matter are spiraling in at odd angles, colliding mid-fall and triggering violent explosions. Others propose an even wilder idea, that the black hole might be shredding a neutron star, tearing it apart piece by piece and igniting gamma rays with each bite. Then there's the timing puzzle. Unlike the steady heartbeat of Juarez 1915, V404 Cygni's outbursts are completely unpredictable, sometimes years apart, sometimes decades. One leading theory points to its accretion disk behaving like a clogged drain, pooling material until the pressure becomes unbearable, then releasing it all in a cataclysmic surge. But why do some black holes flare like this while others stay quiet? Is it a matter of size, spin, or something we haven't even considered? Every flicker from V404 Cygni forces us to rethink what black holes are capable of. They're not just passive voids, they're laboratories of extreme physics, where magnetic fields twist into knots and matter burns brighter than quasars. And if we can decode why these gamma-ray flares erupt, why they flicker, stall, and reignite, we might finally understand the turbulent weather patterns of spacetime itself. One thing's certain, when a black hole like this one speaks, the universe listens. Stephen Hawking's greatest theoretical breakthrough wasn't about what black holes destroy, it was about what they might create. Hawking radiation, the idea that black holes slowly evaporate by leaking particles into space, turned our understanding of these cosmic voids upside down. According to quantum theory, pairs of virtual particles constantly flicker in and out of existence near the event horizon. Normally, they annihilate each other instantly. But if one falls into the black hole while the other escapes, the result is a faint whisper of radiation, a black hole's silent scream as it loses mass over eons. The math is elegant. The problem, no one's ever seen it. That might be about to change. Astronomers have begun chasing infrared ghosts, mysterious heat signatures lingering around ancient black holes that shouldn't exist under classical models. Take a 2620, a dormant black hole drifting through a nearby galaxy cluster. It's surrounded by a faint infrared glow with no visible source, as if something's gently warming the space around it. Could this be Hawking radiation in action? The numbers line up eerily well. Smaller primordial black holes, theoretically forged in the chaos of the Big Bang, would evaporate faster, and their final moments should unleash a burst of infrared energy matching these unexplained signals. But detecting Hawking radiation is like trying to hear a whisper in a hurricane. The cosmic microwave background, the afterglow of the universe's birth, drowns out all but the strongest signals. Some scientists propose hunting for dying black holes in regions where the background noise is unusually quiet, like the voids between galaxy clusters. Others suggest looking for subtle distortions in the radiation itself, telltale spikes in specific frequencies that would betray a black hole's evaporation. The stakes couldn't be higher. If we ever capture Hawking radiation's fingerprint, it would bridge Einstein's gravity with quantum mechanics, unlocking secrets about spacetime's fundamental fabric. Until then, those infrared whispers remain a tantalizing maybe, a cosmic hide-and-seek game where the prize is nothing less than a unified theory of physics. And every unexplained heat signature brings us one step closer to catching a black hole in the act of vanishing. Some black holes don't just shine, they sing. But their songs arrive in fractured layers, like cosmic echoes bouncing through the corridors of twisted spacetime. Take Maxi J 1820 plus 070, a black hole 35,000 light-years away that stunned astronomers with its bizarre light show. Every X-ray flare it emitted came with a ghostly afterimage, appearing seconds to minutes later as if the universe itself had hit the reverb button. These weren't random artifacts, they followed precise mathematical patterns, predictable yet impossible under normal physics. The leading explanation reads like science fiction. We might be hearing the same blast of energy twice, with the delay caused by light taking different paths around the black hole's gravitational whirlpool. Imagine tossing a stone into a pond near a drain. Most ripples flow outward, but some get sucked toward the drain, circling it before finally escaping. That's how spacetime warps around a black hole. Some light escapes directly, while other photons get dragged into orbital loops before emerging later. The result, an eerie cosmic echo chamber, but not everyone's convinced. Some researchers argue these delays could reveal unseen companions, perhaps neutron stars or even smaller black holes hidden in the accretion disk's glare, their gravity subtly altering the emissions. Others propose even wilder ideas, like light scattering off previously unknown structures in the disk itself, structures that warp and vanish as matter churns violently near the event horizon. The data from Maxi J 1820 remains tantalizingly ambiguous. The echo's timing matches predictions from both warped spacetime models and hidden object scenarios with unsettling precision. Here's where things get even stranger. Some echoes arrive with subtle energy shifts, their light slightly redder or bluer than the original flare. That's the hallmark of extreme gravity at work, Einstein's redshift effect in action. Yet in the same dataset, other echoes show no shift at all, muddying the waters further. It's as if the black hole is mixing its signals, blending multiple phenomena into one perplexing symphony. What's at stake goes far beyond solving a single black hole's mystery. If spacetime warping definitively explains these echoes, it gives us a new tool to measure black hole spin and mass with unprecedented accuracy. But if hidden objects are the culprit, we've stumbled upon an entirely new class of binary systems, ones where the partner hides in plain sight, masked by the primary black hole's glare. Either outcome forces us to rewrite chapters in astrophysics textbooks. Until then, Maxi J 1820's delayed whispers remain one of space's most hypnotic riddles, a reminder that even light can't escape a black hole's grip without leaving traces of its ordeal. Deep in the heart of galaxy clusters, where gravity weaves its most intricate webs, black holes are broadcasting signals that shouldn't make sense unless they're tangled up with the universe's greatest ghost. Dark matter, the invisible scaffolding that holds galaxies together, might be leaving fingerprints on these gravitational beasts in ways we're only starting to detect. Take the Bullet Cluster, where two galaxies collided and their black holes became cosmic signposts. X-ray emissions from these black holes don't just trace the visible matter, they eerily mirror the invisible dark matter's distribution, mapped through gravitational lensing. It's as if the black holes are whispering secrets about something we can't even see. Theories abound. One radical idea suggests black holes could be shredding dark matter particles like cosmic paper in a shredder. If certain types of dark matter, like weakly interacting massive particles or WIMP, collide near a black hole's event horizon, their annihilation might spark gamma-ray flares with distinct energy signatures. We've already spotted unexplained spikes in gamma radiation near supermassive black holes, like the one in galaxy M87. These bursts don't match any known stellar process, but they do align with predictions for dark matter annihilation. The math is tantalizing. If just 1% of a black hole's energy output came from devouring dark matter, it would explain these anomalous signals perfectly. Then there's the capture theory. Imagine dark matter particles normally flitting through space unnoticed, getting snagged in a black hole's gravitational web. Over millennia, they could accumulate in dense halos around the event horizon, warping the accretion disk's behavior. Some astronomers argue this might explain why certain black holes flare unpredictably. Their dark matter reservoirs could periodically collapse inward, fueling violent outbursts. Others point to the strange, missing pulsar problem near the Milky Way center, where fewer neutron stars emit radio waves than expected. Could an invisible swarm of dark matter around Sagittarius, a star, be muffling their signals? The implications are staggering. If black holes truly interact with dark matter, they're not just cosmic vacuum cleaners, they're detectives revealing the invisible architecture of the universe. Every anomalous signal could be a clue, a breadcrumb leading us closer to solving dark matter's centuries-old riddle. And if we're right, the darkest places in space might finally help us shed light on the darkest stuff in existence. Some of the universe's most haunting cosmic specters aren't black holes themselves, but their severed limbs, drifting through the void like phantom limbs glowing with ghostly light. Meet the orphan jets, colossal beams of energy that appear completely untethered from their sources, as if the universe forgot to turn off the lights. The most famous of these, Hani's Vorwerp, stunned astronomers when it was discovered in 2007. A glowing green cloud 65,000 light-years across, lit by a quasar beam that had been dead for at least 100,000 years. Here's the spine-tingling part, the supermassive black hole that powered it, lurking in galaxy IC 2497, shows no signs of current activity. It's like finding a flashlight still shining in a forest long after its batteries were removed. These orphan jets rewrite the rules of black hole behavior. Normally, relativistic jet streams of plasma accelerated to near light speed shoot continuously from active black holes, aligning neatly with their spin axes. But Vorwerp's jet bends at impossible angles before terminating in that eerie glow, suggesting something violent interrupted its flow. One theory points to intergalactic winds, colossal gusts of gas moving at thousands of kilometers per second. That could have physically pushed the jet off course like a cosmic garden hose caught in a hurricane. Another possibility involves the black hole's spin axis suddenly flipping, perhaps during a merger with another supermassive black hole, leaving its jet stranded mid-flight while fresh emissions blasted out in a new direction. The timelines make these jets even more baffling. Quasar beams typically fade within centuries as their black holes run low on fuel. Yet Vorwerp's glow persists after millennia, sustained by some unknown mechanism that keeps its gas ionized without an obvious power source. Some researchers speculate these orphan jets might be interacting with previously invisible reservoirs of intergalactic hydrogen, their energy transferring gradually like heat spreading through water. Others wonder if we're seeing light echoes, photons bouncing off ancient dust clouds that act like interstellar delay mirrors, creating the illusion of lingering energy where none exists. What's certain is that these severed jets challenge our entire understanding of black hole lifespans. They hint at violent, unpredictable chapters in galactic history, times when supermassive black holes didn't just flicker out quietly, but went out screaming, their death throes leaving behind luminous scars across the cosmos. And if orphan jets are more common than we thought, they might be the universe's way of preserving black holes past fury in celestial amber, waiting for us to decode their stories. Every disconnected beam is a time capsule, carrying whispers from an era when their creators reshaped galaxies, then vanished without a trace, the deeper mystery. We've likely missed countless orphan jets because they don't behave like active black hole emissions. Their light spreads diffusely, lacking the sharp, focused profiles astronomers typically search for. New surveys using machine learning to spot these ethereal wisps have already uncovered dozens of candidates, each with its own twisted geometry and enigmatic glow. Some appear as perfect arcs, bending around invisible gravitational lenses. Others sprawl chaotically, their structures suggesting multiple epochs of black hole activity layered over eons. Together, they paint a picture of supermassive black holes as capricious giants, not steady cosmic engines, but temperamental artists flicking brushes of plasma across the universe's canvas, leaving behind masterpieces we're only beginning to see. Perhaps the most humbling realization is that for every Hannes Vorwerp we catch glowing defiantly in the darkness, there may be thousands more whose light has already faded or hasn't reached us yet. These orphan jets force us to confront black holes not as static monsters, but as dynamic actors in an epic cosmic drama, capable of leaving indelible marks long after their scenes have ended. And if we learn to read their fragmented signatures, they might reveal hidden chapters in the life stories of galaxies, including our own. After all, the Milky Way's supermassive black hole, Sagittarius A*, was likely quasar bright in its youth. What ghostly jets might it have left crisscrossing our galactic neighborhood, their light still traveling toward some distant observer's future telescope? The universe keeps its secrets well, but not forever. There's a cosmic game of hide and seek happening across the Milky Way, and black holes are playing dirty. Astronomers have mapped regions where stellar mass black holes should be screaming their presence through blistering X-rays, yet the signals simply aren't there. These missing X-ray binaries defy expectations, lurking in the darkness without the telltale glow of superheated accretion disks. It's like finding an empty seat at a concert when you're certain the ticket was sold. Something fundamental doesn't add up. Take the Cygnus constellation, packed with young, massive stars perfect for birthing black hole binaries. Models predict at least 30 active X-ray sources should dot this region, but fewer than half have been detected. Where are the others? One possibility is camouflage. Some black holes might be shrouded in thick cocoons of dust, their X-rays absorbed before reaching our telescopes. Imagine wrapping a flashlight in layers of wool. The light still burns, but no one sees it. Observations from the Chandra X-ray Observatory support this, showing faint infrared halos around some quiet black holes that could trace these cosmic dust blankets. But there's a wilder explanation. What if these black holes aren't just hiding, they're starving? Binary systems typically emit X-rays when the black hole strips gas from its companion star, creating a swirling disk of doomed matter. Yet some black holes might orbit their partners at unusually wide separations, only nibbling occasionally like diners at a sparse buffet. Others could have already devoured their stellar meals entirely, leaving nothing left to glow. The weirdest candidates, naked black holes drifting alone after gravitational kicks ejected them from their binary systems entirely, invisible except for rare microlensing events when they warp background starlight. The implications ripple across astrophysics. If even a fraction of missing X-ray binaries are truly dormant, it suggests black holes spend far more time in hibernation than we thought. Perhaps decades or centuries between feeding frenzies. That would rewrite our understanding of galactic evolution, forcing us to reconsider how black holes influence star formation and gas dynamics during their silent phases. It also complicates the hunt for gravitational wave sources. Quieter black holes mean more unseen mergers lurking in the data. Perhaps most intriguing are recent radio surveys revealing faint, persistent emissions from some quiet black holes, whispers where we expected screams. These could be the smoking guns of stealthy accretion, trickles of matter too sparse to heat up but regular enough to sustain weak magnetic fields. Like finding footprints in fresh snow, these radio traces hint at movement where the eye sees only stillness. The universe's darkest predators might be far more patient and far more numerous than we ever imagined. Quasars are supposed to be the universe's most stable lighthouses, supermassive black holes feasting so steadily on gas that their brilliant accretion disks shine with unwavering intensity for millions of years. But something's wrong with the ones that blink. Astronomers have caught a handful of these cosmic giants flickering like faulty light bulbs, their brightness swinging wildly over mere decades, sometimes even months. That shouldn't happen. A black hole weighing billions of suns can't just change its appetite on a human timescale. It'd be like watching a glacier pulse like a heartbeat. Take the case of J0157 plus 0043. This quasar, 9 billion light-years away, dimmed by 20% between 2002 and 2010, then partially rebrightened by 2015. The leading theory, a rogue swarm of debris, perhaps the mangled remains of a devoured star, could be orbiting just outside the event horizon, periodically blocking our view like a cosmic Venetian blind. Simulations show dense clouds spiraling inward could create these precise dimming patterns, their shadows sweeping across the accretion disk in years rather than eons. But there's a catch. The shadows should distort as they move, stretching and warping under the black hole's extreme gravity. Yet some flickering quasars dim uniformly, as if someone's turning down a dial. That's where the sputtering disk theory comes in. Imagine the quasar's accretion disk, normally a smooth, red-hot whirlpool of gas, developing turbulent bubbles like boiling water. Magnetic instabilities could cause sections of the disk to collapse inward prematurely, starving the black hole momentarily before fresh gas spirals in to reignite the glow. It's the equivalent of a fire hose kinking and unkinking, with each kink dimming the quasar's output. Some researchers argue this might explain why certain quasars flicker in semi-regular cycles, their brightness wobbling like a top losing spin. The most unsettling cases, though, show no pattern at all. Quasar SDSS J0942 plus 090, for instance, doubled in brightness over just 5 years before fading again twice. No known debris model fits. Here's where things get speculative. Could we be seeing the quasar's jet, normally a steady particle beam, wobble violently due to interactions with another supermassive black hole nearby? Or perhaps evidence of rare disk tearing, where misaligned gas streams rip the accretion disk into warped, unstable rings that intermittently feed the monster. These flickering giants force us to confront how little we truly understand about quasar mechanics. Every erratic pulse is a challenge to the textbook image of serene, eternal behemoths. Instead, they suggest supermassive black holes might have moods, cycles of famine and feast written in light, waiting for us to decode their irregular rhythms. And if we're right about the causes, it means the universe's brightest objects are also its most temperamental. The universe isn't just speaking, it's humming. Beneath the violent crashes of colliding black holes that LIGO famously detects, there's something far subtler, a faint, persistent rumble of low-frequency gravitational waves. This cosmic background noise, first hinted at in 2021, isn't the work of individual collisions. It's a choir of countless supermassive black hole binaries, each orbiting its partner for millions of years before merging, their gravitational waves blending into a chorus that permeates spacetime itself. The pitch is unimaginably deep oscillations so slow they take years, even decades, to complete a single cycle. If a typical LIGO detection is a cymbal crash, this hum is the distant roll of thunder, always present but just beyond hearing. Not everyone agrees on its origins. Some theorists argue these waves could stem from something even grander, the collective vibrations of primordial black holes, forged in the Big Bang's first seconds and now woven into the fabric of the cosmos. Others propose a wilder source, cosmic strings, hypothetical defects in spacetime left over from the universe's birth, vibrating like guitar strings plucked by gravity. The debate hinges on the hum's peculiar uniformity. Unlike random noise, it carries faint but coherent patterns, as if encoded with information. Could this be the universe's way of broadcasting the distribution of supermassive black holes across time? Or evidence of something stranger lurking between galaxies? Detecting this hum pushes our technology to its limits. LIGO interferometers designed to catch high-frequency ripples are deaf to these ultra-low tones. Instead, astronomers turn to an ingenious cosmic tool, pulsars. These spinning neutron stars act as celestial metronomes, their radio pulses arriving on Earth with near-perfect regularity. By monitoring subtle timing shifts across dozens of pulsars for over a decade, researchers spotted the telltale stretching and squeezing of spacetime signatures of passing gravitational waves. The effect is minuscule, shifting pulse arrival times by mere nanoseconds, but the consistency across multiple pulsars is what makes the case compelling. The implications are staggering. If confirmed as black hole binaries, this hum would reveal a hidden population of supermassive pairs lurking in galactic cores, each waiting for their eventual collision. Their orbital dynamics could unlock secrets about galaxy formation, showing how mergers shape cosmic structures over billions of years. But if the signal stems from primordial black holes or cosmic strings, it would rewrite our understanding of the universe's infancy, offering clues about physics at energies far beyond what any particle accelerator could reach. For now, the hum remains a tantalizing whisper just above the threshold of detection. Future pulsar timing arrays, with more sensitive telescopes tracking hundreds of pulsars, could soon tease out its melody in greater detail. And if we're lucky, that melody might carry harmonies we never expected. A cosmic symphony composed by the darkest objects in existence, played on the strings of spacetime itself. Light isn't just escaping black holes, it's twisting in ways that defy physics. When the Event Horizon Telescope captured the first image of M87 star's shadow in 2019, something hidden in the data sent theorists spiraling. The light around that monstrous void wasn't just glowing. It was polarized, its waves aligned at angles so extreme they shouldn't exist. Polarization normally occurs when light passes through magnetic fields or scatters off particles, creating orderly patterns. But M87 star's light wasn't just organized, it was too organized, with polarization arcs curving like hooks around the event horizon, as if spacetime itself were wrung like a wet towel. The leading suspect, a magnetic vortex stronger than anything we've imagined. Picture the black hole's accretion disk as a cosmic hurricane, with magnetic field lines coiled so tightly they act like spiral staircases for light. As photons climb these stairs, their polarization could twist to match the field structure. But simulations show even this shouldn't produce the razor-sharp angles we're seeing. That's where spacetime torsion comes in, a twist in the very fabric of reality predicted by some quantum gravity theories. If spacetime isn't just bent near black holes but twisted like a corkscrew, it could rotate light's polarization beyond classical limits. It's the difference between bending a beam of light and braiding it. Yet there's a wild card: exotic plasma. The disk around M87 star isn't just hot gas. It's a soup of relativistic particles moving at near light speed. Under these conditions, plasma can form double layers, sheets of opposing charge that act like cosmic mirrors, reflecting and repolarizing light in chaotic ways. Some researchers argue these layers might fold back on themselves near the event horizon, creating feedback loops that amplify polarization to impossible levels. Others point to quantum electrodynamics effects, where virtual particles popping in and out of existence briefly alter light's path. The stakes are cosmic. If space-time torsion is real, it's direct evidence that Einstein's gravity merges with quantum mechanics in black hole extremes. If exotic plasma's to blame, it means accretion disks are far more complex and far more powerful than our models predict. Every new polarization measurement is a clue, a flickering signpost pointing toward truths we've yet to grasp. And as telescopes peer deeper, these twisted beams of light might finally reveal whether black hole's not spacetime itself, or if something even stranger is at play. Ton 618 shouldn't exist, at least, not by the rules we thought governed black holes. This cosmic behemoth, shining from the early universe with the brilliance of 140 trillion suns, breaks every law of cosmic moderation. The problem isn't its size, though its 66 billion solar masses dwarf our Milky Way's central black hole like a whale beside a goldfish. It's the light. According to the Eddington limit, a black hole's radiation should push back on infalling matter, creating a balance that caps its brightness. Ton 618 blasts past that theoretical ceiling like a car with no speedometer, emitting enough energy to vaporize entire galaxies. So how does this monster keep devouring without burning itself out? The answer might lie in chaos we're only beginning to map. Most accretion disks resemble orderly whirlpools with gas spiraling inward in predictable streams. But for supermassive black holes like Ton 618, feeding could be more like a hurricane slamming into a tornado. Simulations show that under extreme conditions, magnetic fields twist the disk into towering, unstable funnel structures that channel gas directly toward the event horizon while letting radiation escape through gaps like steam whistling out of a pressure cooker. This leaky feeding could let black holes briefly exceed Eddington limits without self-destructing, creating short-lived but spectacular outbursts visible across the universe. Then there's the merger hypothesis. When two supermassive black holes collide, their combined accretion disks might temporarily form a hyper-efficient engine, shredding stars and gas clouds into a frenzied buffet. Ton 618 size and luminosity fit neatly with this scenario. It could be the aftermath of a cosmic demolition derby, where two already giant black holes smash together, igniting a quasar that burns brighter than entire galaxy clusters. But the most radical idea challenges the Eddington limit itself. What if the rule based on spherical, steady-state assumptions doesn't apply to these ancient giants? Black holes in the early universe fed on gas far denser than anything in today's cosmos. Under those conditions, radiation might not push back effectively, allowing runaway consumption. Or perhaps the limit does hold, just differently, with the excess energy emerging as gravitational waves or dark matter interactions we can't yet detect. Ton 618 isn't alone. Quasars like SDSS J0100 plus 2802, 12 billion light-years away, show similar defiance. Each one forces us to rethink the physics of gluttony on cosmic scales. Are we seeing violations of fundamental laws, or just the universe reminding us that black holes, like the rules governing them, are far more complex than we ever imagined? The answer may lie not in our model's flaws, but in their incompleteness. After all, we're trying to describe the most extreme objects in existence using equations written for comma corners of reality. The next generation of telescopes could settle the debate. If we catch a super Eddington black hole mid-feeding frenzy, watching how its light flickers and flares, we might finally decode these cosmic anomalies. Until then, Ton 618 stands as both a mystery and a beacon, proof that even the darkest voids can shine light on the universe's deepest secrets. Sometimes the universe doesn't just send signals, it amplifies them, turning whispers into screams. And in some cases, black holes might be the cosmic megaphones. Astronomers have caught bizarre instances where signals, whether X-rays, radio waves, or even gravitational waves, appear unnaturally magnified, as if passing through an invisible amplifier. The most logical explanation, gravitational lensing, where a black hole's immense gravity bends spacetime so drastically that it acts like a warped magnifying glass, distorting and brightening light from objects behind it. But what happens when the magnification defies even that explanation? When the signals aren't just bent, they're changed. Take the case of PS110 ADI, a mysterious flash from a distant galaxy initially mistaken for a supernova. Its light curve didn't match any known stellar explosion. Instead, it brightened too symmetrically, too uniformly, as if something were stretching and focusing its emission over time. The culprit, a supermassive black hole drifting between the source and Earth, its gravity not merely lensing the light but reshaping it. Unlike typical lensing, which produces duplicate or smeared images, this event suggested the black hole's gravitational field was acting like a tunable filter, enhancing specific frequencies while suppressing others. It's the difference between looking through a funhouse mirror and a prism. One distorts, the other transforms, but gravitational lensing can't explain every anomaly. Some lensed signals exhibit flickering patterns too rapid for a black hole's steady curvature. One theory points to rare, chaotic lensing, where turbulence in the black hole's accretion disk creates fluctuating hotspots in spacetime itself. Imagine light traveling through a maze of shifting funhouse mirrors, each turn subtly altering the signal's intensity and timing. Other signals show energy boosts inconsistent with pure lensing, as if the black hole isn't just bending light but injecting extra energy into it. Could magnetic fields coiled like springs near the event horizon be accelerating particles mid-flight? Or is there an unknown interaction between lensed photons and the black hole's quantum atmosphere? Then there's the outlier, signals that appear lensed but with no detectable lens, no intervening black hole, no massive galaxy, just unexplained magnification, as if space itself has hidden wrinkles we can't map. These ghost lenses have led some theorists to speculate about primordial black holes, ancient relics from the Big Bang too small and dark to spot directly. Others wonder if dark matter's invisible scaffolding could be twisting space-time in ways we've yet to model. The implications stretch beyond astrophysics. If black holes can selectively amplify signals, they might be the universe's natural broadcast towers focusing messages across cosmic distances. And if the anomalies hint at new physics, they could redefine how we see everything from distant quasars to the cosmic microwave background. For now, these lensed whispers remain tantalizingly out of reach footprints of a universe more intricate, more layered than we ever dreamed. Most cosmic objects follow a simple rule: when they feed faster, they shine brighter. But black holes love to break rules, and the anti-correlation effect is one of their most baffling tricks. Picture this as a black hole's accretion disk flares with X-rays, the surrounding corona, a halo of superheated particles just above the disk, should blaze in tandem. Instead, it dims. It's like watching a bonfire grow while its heat mysteriously fades, defying every expectation of how energy behaves. This eerie inverse relationship has been spotted in multiple black holes, most notably in the well-studied system GX339-4, where every X-ray spike in the disk corresponds to a precise dip in the corona's emission. The numbers don't lie, but the physics behind them might. One explanation points to cosmic shadow play. As the inner disk puffs up during feeding frenzies, it could physically block our view of the corona, casting a temporary eclipse. Simulations show this works, but only for specific viewing angles. The timing's also off. The corona dims instantly with disk brightening, while shadowing should lag slightly as material moves. That mismatch has led to a wilder idea: energy theft. Magnetic fields threading the disk might act like siphon hoses, funneling energy away from the corona and into the black hole's jets. Imagine a power grid where turning on one neighborhood browns out another, except here, the grid is woven from spacetime itself. The plot thickens with discosismology. Yes, that's a real term. Just as earthquakes reveal Earth's inner structure, vibrations in the accretion disk could trigger resonant waves that redistribute energy. Some modes might channel power inward, starving the corona in rhythmic pulses. Others could launch shocks that collide with the corona, dissipating its energy like ocean waves smashing a cliff. Remarkably, these models predict anti-correlation patterns matching actual observations, down to the millisecond delays between disk and corona changes. Yet the most tantalizing clues come from black holes that flip the effect. In Maxi J 1543-564, the corona brightens first, followed by disk dimming. This reversal hints at an even stranger dynamic. The corona might be the puppet master, not the victim. If its magnetic loops suddenly snap, releasing stored energy in a flare, they could overpressure the disk below, momentarily stifling its glow. It's a cosmic feedback loop where cause and effect blur, leaving us wondering which part of the black hole's anatomy is really in charge. Each of these theories has its merits, but none explain every case cleanly. That inconsistency might be the real revelation. Black holes don't operate on a single, universal rulebook. Their feeding habits could depend on spin rate, magnetic field geometry, even the chemical makeup of their meals. The anti-correlation puzzle isn't just a curiosity, it's a backstage pass to the most violent energy exchanges in the universe, where the rules get rewritten daily. And until we crack it, every flickering black hole remains both a riddle and a Rosetta Stone, hiding the truth in plain sight. Black holes aren't just cosmic vacuum cleaners, they're messy eaters, leaving behind crumbs in the form of glowing accretion disks. But some have gone suspiciously clean, their once bright rings of superheated gas vanishing without explanation. These ghost disks defy everything we know about black hole feeding habits. Take a 62, a supermassive black hole lurking in a quiet galaxy cluster. Its X-ray emissions suggest it should be surrounded by a bustling disk of infalling matter. Yet optical and infrared observations show only eerie darkness. It's as if someone turned off the cosmic kitchen light but left the stove burning. Theories abound about where these disks went. One possibility is evaporation, not of the black hole itself, but of its meal. Just as puddles shrink under sunlight, accretion disks might dissipate when exposed to intense radiation from nearby stars or other black holes. Simulations show that in dense galactic environments, ultraviolet light from young, massive stars could strip gas atoms from a disk's outer layers, starving the black hole over millennia. But a 62 sits in relative isolation, making this scenario unlikely. That's led researchers to consider more exotic explanations like dark matter interference. If certain types of dark matter particles interact with ordinary matter even weakly, they might scatter the disk's gas particles, disrupting the orderly spiral into the black hole. Imagine trying to fill a bathtub while someone keeps poking holes in the pipe. Then there's the transition theory. Some black holes might oscillate between two states, sometimes feeding voraciously and shining brightly, other times entering a low-hard state where the disk fragments into clumps. These clumps, too sparse to glow continuously, might only flare when they occasionally collide or fall inward. The black hole in galaxy Markarian 11018 behaves exactly this way, flickering unpredictably as if chewing on cosmic popcorn rather than slurping a smooth gas stream. But the strangest cases show no disk at all, not even fragments. These black holes shine brightly in X-rays but remain dark at all other wavelengths, suggesting their accretion disks might have collapsed inward so completely that only the innermost region, a tiny, scorching ring just outside the event horizon, still radiates. It's like seeing the glow of a furnace through a keyhole with no sign of the fuel feeding it. The implications ripple across astronomy. If ghost disks are common, we might be grossly overestimating how much matter black holes consume and misunderstanding their role in galaxy evolution. These cosmic phantoms could also explain why some supermassive black holes grow so massive so quickly in the early universe. If their disks periodically vanish from view, we might be missing crucial chapters in their feeding history. Every missing disk is a cosmic crime scene, and we're just learning to read the fingerprints. Some black holes don't just roar, they sing in deep, slow notes that stretch across human lifetimes. Take OJ-287, a supermassive black hole 3.5 billion light-years away that's been winking at us like a cosmic metronome for over a century. Every 12 years, like clockwork, it erupts in brilliant optical flares, but here's the catch. These aren't random outbursts. They arrive in pairs, separated by 1 to 3 years, followed by eerie silence until the next cycle begins. It's as if something vast and unseen is winding an intergalactic music box, playing the same haunting melody on a scale we can barely comprehend. The leading theory paints an epic picture, a dance of two supermassive black holes locked in a death spiral. The primary black hole, weighing 18 billion suns, could have a smaller partner, a mere 150 million solar masses orbiting it in a highly elliptical path. As the smaller black hole plunges through the primary's accretion disk twice per orbit, it would kick up titanic shock waves, heating the gas to white-hot temperatures and triggering those predictable flares. But the real magic lies in the dance's precision. General relativity predicts such a system would exhibit absolute precession. The orbit itself should rotate like a spirograph, shifting slightly with each pass. Remarkably, OJ-287's flare timing matches this prediction to near perfection, suggesting we're witnessing Einstein's equations play out in real time across cosmic distances. Yet not all astronomers are convinced. Alternative explanations point to disk warping. The primary black hole's accretion disk might not lie flat but wobble like a spinning plate, its misaligned sections periodically dipping into hotter regions and flaring up. Others propose a slingshot scenario where a single black hole's jet precesses over decades, sweeping its beam across our line of sight like a galactic lighthouse. The debate hinges on subtle clues buried in the flare's spectra. Binary mergers should produce clean, thermal peaks as gas heats uniformly, while disk warping could leave jagged spectral fingerprints from turbulent magnetic fields. What makes OJ-287 truly extraordinary is its timescale. Unlike fleeting gamma-ray bursts or sudden quasar ignitions, this signal unfolds on a time frame humans can witness directly, if patiently. Early photographic plates from the 1890s show the same 12-year pattern we observe today, making it one of astronomy's rarest treasures, a celestial phenomenon that bridges generations. The next double flare, predicted for 2022, could settle decades of debate if the smaller black hole's passage tears a particularly bright wound in the disk. Until then, this cosmic siren keeps singing its slow, gravitational waltz, reminding us that some of the universe's grandest dramas unfold not in seconds but in centuries. The universe has its own version of sonar, short, sharp bursts of gravitational waves that ping across space like echolocation clicks. Scientists call them chirps, and they're some of the most perplexing signals ever detected. Unlike the deep, rumbling waves from colliding black holes that LIGO typically catches, these chirps register at far higher frequencies, up to 1,000 Hz, vanishing almost as soon as they appear. The strangest part, there's no visible collision to explain them, no merging neutron stars, no clashing black holes, just blips of warped space-time with no obvious source, as if the cosmos itself is tapping on reality's window. One explanation sends shivers down physicists' spines: primordial black holes. These hypothetical relics, forged in the Big Bang's inferno, could be far smaller than stellar black holes, some no heavier than asteroids. If two of these ancient specks collided today, their tiny event horizons would whip space-time into ultra-high frequency ripples before vanishing without leaving behind the usual glow of debris or light. It's like hearing the splash of two raindrops merging in a dark ocean but never seeing the water. The math checks out. Primordial black holes would chirp at exactly these frequencies before evaporating into quantum foam. Yet there's a catch. Primordial black holes should be everywhere if they exist, yet we've found no direct proof. That's led some theorists down an even stranger path: exotic compact objects, or ECO. These aren't black holes at all, but ultra-dense bodies made of hypothetical matter that stops just short of collapsing into a singularity. Picture a neutron star's denser cousin, wrapped in a thin shell of exotic particles. When two ECOs merge, they'd chirp like black holes, but with subtle deviations in the waveform, tiny hiccups betraying their true nature. Some models even suggest ECOs could leave behind remnants after merging, violating Hawking's no-hair theorem and rewriting our understanding of cosmic demolition. The most tantalizing chirps, though, defy both explanations. A handful detected by LIGO and Virgo show bizarre overtones, harmonic frequencies superimposed on the main signal like ghostly echoes. If confirmed, these overtones could hint at structures beyond the event horizon, perhaps quantum fuzz predicted by string theory, or even wormholes momentarily bridging distant regions of spacetime. Imagine hearing not just the collision but the reverberations of an entire hidden dimension. Every unexplained chirp is a cosmic breadcrumb leading us toward truths we've barely glimpsed. Whether they're primordial black holes, exotic matter, or something beyond our current physics, one thing's certain: the universe is pinging us with secrets, waiting for someone to decode their meaning. And if we listen closely enough, these fleeting signals might reveal realities we never dared to imagine. Black holes aren't supposed to glow, especially not in infrared. Yet scattered across the universe, astronomers keep finding these gravitational monsters wrapped in mysterious halos of heat, radiating far more infrared light than any known physics should allow. Take NGC 4261, a supermassive black hole 60 million light-years away with an infrared excess so extreme it outshines its entire host galaxy. At first glance, it's easy to brush this off as ordinary dust. After all, black holes often chew through clouds of debris, heating them until they glow. But the numbers don't add up. The temperature profiles are all wrong. This isn't the uniform warmth of interstellar dust. It's a strange, patchy heat, concentrated in regions with no visible matter to fuel it. One theory points to hidden stellar nurseries. Intense radiation from the black hole's accretion disk could trigger star formation in surrounding gas clouds, their newborn stars smothered under thick blankets of dust. These obscured stars would emit copious infrared light while remaining invisible to optical telescopes, like campfires seen through dense fog. Supporting this, some galaxies with infrared excess show subtle hints of ionized gas, potential fingerprints of massive stars burning within the gloom. But NGC 4261's heat signature is too widespread and structured for random star formation. The excess forms distinct rings and spirals, following patterns more suggestive of something intrinsic to the black hole itself. That's where Hawking radiation analogs enter the picture. While true Hawking radiation from supermassive black holes is too faint to detect, some theorists propose similar quantum effects could occur at macroscopic scales. Magnetic reconnection events near the event horizon might generate virtual particle showers, their energy dissipating as infrared rather than escaping as radiation. Others speculate about graviton's hypothetical particles mediating gravity, leaking energy into surrounding space-time like slow-acting friction. These processes wouldn't produce the textbook Hawking effect, but could mimic its infrared consequences, turning black holes into unexpected cosmic radiators. Then there's the wild card: black holes as dark matter factories. Certain dark matter candidates, like weakly interacting massive particles, could accumulate in dense halos around black holes. Their occasional annihilations would release energy predominantly as infrared photons, creating precisely the kind of excess we observe. Intriguingly, NGC 4261's infrared halo aligns with predicted dark matter distributions for its host galaxy's size, a coincidence too tantalizing to ignore. The debate rages because each explanation carries world-changing implications. Hidden star formation would rewrite our understanding of galactic nuclei as sterile voids. Quantum effects would offer a backdoor to probe gravity's quantum nature, and dark matter interactions that could finally crack open the universe's most persistent mystery. For now, these infrared wraiths keep their secrets, glowing silently in the dark, reminders that even black holes, the universe's darkest objects, can't help but leave traces of their hidden lives. Every black hole we've ever discovered has one defining feature: an event horizon, the point of no return where even light surrenders to gravity's grip. But what if some of these cosmic titans are hiding in plain sight without their signature shrouds? Meet the naked singularity hypothesis, a radical idea that certain black holes might not bother with event horizons at all, leaving their infinitely dense cores exposed to the universe. It's a notion that would make Einstein shudder, violating the cosmic censorship conjecture, a principle suggesting nature abhors a bare singularity. Yet astronomers keep stumbling upon bizarre signals that fit no other explanation. Take the case of Swift J1644 plus 5734, a black hole candidate that flared violently in 2011. Its X-ray emissions followed patterns eerily similar to those expected from an accretion disk, but with one glaring anomaly. The light curves lacked the telltale signatures of an event horizon's influence, as if the radiation originated from a singularity floating naked in space. Ordinarily, as matter spirals toward a black hole's event horizon, its light stretches and dims in predictable ways, a phenomenon called relativistic redshift. Swift J1644's emissions didn't redshift, they just vanished, as though whatever produced them wasn't obscured by an event horizon's shadow but simply ceased to exist. Skeptics argue these signals could stem from exotic magnetars, neutron stars with magnetic fields so intense they mimic black hole behavior. Others point to relativistic jets viewed head-on, their beamed emission masquerading as a singularity's glow. But one observation throws a wrench in these explanations: the lack of spin modulation. Black holes warp spacetime so dramatically that their rotation imprints rhythmic flickers on surrounding matter. Naked singularities, unburdened by an event horizon, wouldn't produce this effect, precisely what we've detected in a handful of perplexing systems like Jaro J1655-40. The implications are staggering. If naked singularities exist, they'd be cosmic laboratories for probing quantum gravity, their exposed cores offering a front-row seat to physics beyond Einstein's equations. They might even explain dark energy's origins. Some models suggest naked singularities could leak energy from other dimensions, fueling the universe's accelerated expansion. But the real puzzle is why we don't see more of them. If singularities can shed their event horizons, why aren't they littering the cosmos? Perhaps they're hiding in the noise. Detecting a naked singularity requires catching its radiation in the act of escaping something that should be impossible if general relativity holds. Yet gravitational wave detectors like LIGO might soon settle the debate. Collisions involving naked singularities would produce chirps subtly distinct from black hole mergers, their waveforms lacking the ring-down phase where event horizons stabilize. Until then, these enigmatic signals remain both a tantalizing possibility and a glaring challenge to everything we thought we knew about the universe's most extreme objects. One thing's certain: if even a single naked singularity is confirmed, it wouldn't just rewrite astrophysics textbooks, it'd tear them to shreds. Black holes are cosmic tops, spinning with such relentless precision that astronomers use their rotations as universal clocks until they stutter. Like a record skipping mid-play, certain black holes suddenly change their spin rates without warning, leaving behind a trail of baffled scientists. GX339-4, a well-studied stellar mass black hole in our galaxy, has pulled this trick multiple times. Over the span of just days, its rotation slowed by nearly 2% before resuming its normal rhythm. That shouldn't be possible. A black hole's spin is governed by the unbreakable conservation of angular momentum, the same law that keeps ice skaters twirling smoothly as they pull their arms in. So what could jolt such a massive object off its axis? One explanation reads like cosmic vandalism, a rogue star smashing into the accretion disk. Picture a pebble thrown into a spinning fan blade. The impact wouldn't just dent the blade, it could momentarily stall the motor. For GX339-4, a stellar intruder plunging through its disk at the wrong angle might transfer enough momentum to briefly break the black hole's spin. The math supports this. If the star carried sufficient mass and velocity, the collision could explain the glitch's abruptness. But there's a catch. No accompanying flare or debris from such a violent encounter has ever been detected. Where's the stellar wreckage? That missing evidence has led theorists to a wilder possibility: quantum spacetime foam. At the smallest scales near the event horizon, space itself might not be smooth as Einstein imagined. Instead, it could froth with microscopic bubbles of fluctuating geometry regions where the fabric of reality briefly tightens or loosens. If this foam interacts with the black hole's ergosphere, the region just outside the event horizon where space gets dragged inexorably along with the spin, it might create temporary stickiness. Think of it like a spinning top encountering patches of friction on a table. Some areas resist more than others, causing subtle hiccups in rotation. The smoking gun could lie in the timing. Collision-induced glitches should be random, following the chaotic distribution of stars in a black hole's vicinity. Quantum foam glitches, though, might cluster around specific energy thresholds tied to Planck scale physics. Recent analysis of GX339-4's behavior reveals something intriguing. Its stutters aren't entirely random. They show faint statistical patterns, like dice subtly favoring certain numbers over long rolls. That doesn't rule out collisions entirely. Space is messy, but it does open the door to something far stranger. What's at stake isn't just why one black hole stumbles. If quantum foam leaves fingerprints on spin rates, it means we've been handed a backstage pass to quantum gravity itself, a chance to observe how spacetime behaves when crushed to its smallest possible scales. Conversely, if colliding stars are the culprits, we're missing a key piece of galactic demographics, a hidden population of wanderers prowling too close to these gravitational monsters. Every glitch is a cosmic tremor, rippling through both our models and our understanding of the universe's most extreme environments. And until we decode them, black holes will keep spinning their mysteries just out of reach. Cygnus X1's particle jets don't just defy expectations, they mock them. This iconic black hole, 7,000 light-years away, launches beams of plasma so energetic they shouldn't exist under conventional physics. Each jet punches outward at nearly the speed of light, carrying enough raw power to outshine entire star clusters. But here's the twist. The math says these jets drain more energy than the black hole's accretion disk could possibly supply. It's like watching a car race across the desert without a fuel tank somewhere. An invisible engine is at work. The leading theories read like sci-fi. One radical idea suggests black holes like Cygnus X1 might be tapping into dark energy, the mysterious force accelerating the universe's expansion. Imagine the jets as cosmic siphon hoses, drawing power not from the disk but from spacetime itself as it stretches. If true, it would mean black holes aren't just consuming matter, they're harvesting the vacuum of space, converting its inherent energy into visible outbursts. Supporting this, Cygnus X1's jets show bizarre fluctuations in intensity that align with theoretical models of dark energy interactions. When the jets flare, they don't just brighten, they pulse in rhythmic waves as if resonating with something far larger than the black hole itself. Then there's the extra-dimensional angle. String theory proposes that gravity could leak into higher dimensions, weakening its observed strength in our 3D universe. If Cygnus X1's jets are channeling even a fraction of this hidden gravitational potential, it could explain their outrageous energy budgets. Picture the black hole as a dam holding back a multidimensional reservoir. The jets might be cracks in that dam, venting pressure from realms we can't see. Some researchers point to the jets' unusual polarization patterns as possible evidence. Their light waves twist in ways that don't match known magnetic field behaviors, but align eerily well with simulations of higher dimensional turbulence. Yet not all clues point beyond known physics. An alternative camp argues the secret lies in the black hole's spin. Cygnus X1 is a rapid rotator, whipping spacetime around it into a vortex. This spin could act like a flywheel, storing colossal rotational energy that the jets periodically tap. General relativity predicts such systems might launch jets through a process called the Blandford-Zeenagic mechanism, where the black hole's twisting magnetic fields extract spin energy directly. The catch, even this model falls short of explaining the jet's peak outputs unless Cygnus X1's spin rate is even faster than measured, teetering on the theoretical maximum. What makes these jets truly paradoxical isn't just their energy, it's their precision. Unlike chaotic quasar beams, Cygnus X1's jets maintain razor-straight trajectories across light years, resisting the dispersion that should scatter them into useless fog. Something is focusing them with unnatural clarity. Magnetic fields could play a role, but the required strength would shatter any known material. That's led some to propose quantum entanglement effects. Particles in the jets might remain mysteriously linked, their coordinated motions keeping the beam cohesive against all odds. Every anomaly in these jets forces us to reconsider what black holes are capable of. Whether they're drawing power from dark energy, higher dimensions, or some undiscovered facet of spacetime itself, one thing is clear: the universe has handed us a riddle wrapped in a beam of light. And until we crack it, Cygnus X1's jets will keep blazing through the cosmos, taunting us with their impossible brilliance. In the static of the cosmic dawn, the universe's first flickers of light, lurks a signal so strange it made astronomers question their most fundamental assumptions. The Edge's detection, captured in 2018, revealed a deep dip in the radio spectrum at 78 MHz, a fingerprint of hydrogen gas cooling against the backdrop of the early cosmos. But the cooling was too extreme, too rapid, defying every simulation of how the infant universe should behave. There's only one problem: nothing in the standard model can explain it. Unless, of course, we're hearing the echoes of primordial black holes, ancient, tiny, and evaporating in the darkness. The math is tantalizing. Primordial black holes, forged in the Big Bang's chaotic first seconds, could have peppered the early universe like cosmic shrapnel. If they were the right massa, around 20 times the weight of a mountain, they'd be evaporating right around the era edges probed. Hawking radiation from their demise would bathe surrounding hydrogen gas in a chilly glow, supercharging its cooling rate. It's like dropping ice cubes into a lukewarm bath. The temperature plummets unnaturally fast. The timing aligns eerily well. But here's the catch. For this to work, primordial black holes would need to be absurdly abundant, making up a significant fraction of dark matter. And that opens a Pandora's box of contradictions with other cosmic observations. Not everyone's convinced. Alternative explanations range from exotic dark matter interactions particles that siphon thermal energy from hydrogen, to radical revisions of the laws of atomic physics. Some theorists argue that if dark matter carries even a slight electric charge, it could scatter hydrogen atoms like billiard balls, cooling them through sheer friction. Others propose that the universe's magnetic fields were far stronger in its infancy, altering how hydrogen absorbed and emitted radio waves. Yet none of these ideas fully account for the edge's signal's depth and shape without straining other known physics. Then there's the wild card. What if primordial black holes didn't just evaporate but interacted? Simulations show that if these black holes collided or clustered in the early universe, their gravitational wakes could stir hydrogen gas into frenzied ripples, amplifying cooling in hotspots. We might be seeing the ghostly imprint of entire black hole swarms flickering out of existence, their collective death throes tweaking the cosmic thermostat. The signal's uneven structure, subtle bumps within the broad dip hints at this kind of messy, large-scale turbulence. Edges remains controversial. Follow-up observations have failed to confirm the signal with the same clarity, leaving astronomers divided. But if it is real, and if primordial black holes are the culprits, it would rewrite cosmic history. These tiny, ancient monsters could have seeded the first stars, sculpted the distribution of galaxies, or even birthed the supermassive black holes lurking in today's galactic cores. Every unexplained wisp of radiostatic from the dawn of time might carry their faint farewells, whispering secrets about the universe's darkest, oldest inhabitants. Until new telescopes peer deeper into the cosmic sunrise, this eerie echo hangs in the balance, a puzzle wrapped in the static of creation itself. Einstein's equations left us with two cosmic nightmares: black holes, where gravity crushes matter into oblivion, and wormholes, theoretical tunnels through space-time. But what if these monsters are the same beast wearing different masks? A growing chorus of physicists suspects the signals we attribute to black holes might actually be wormholes in disguise, their differences blurred by quantum entanglement's strange magic. This isn't science fiction, it's the ER=EPR conjecture, a radical idea suggesting that wormholes' Einstein-Rosen bridges might be quantum entanglement's gravitational shadow. Take the strange case of GW150914, a gravitational wave detected by LIGO in 2015. This collision looked textbook at first, two black holes spiraling into one. But the ring-down phase, where the merged object settles into its final form, lasted too long. The signal's echo lingered like a bell struck in a cavern, hinting at something far stranger than a simple singularity. Simulations now show this exact pattern could emerge if the colliding objects were wormholes, their throats vibrating like plucked strings before snapping shut. The key clue: wormholes lack true event horizons, allowing subtle vibrations to escape that black holes would swallow whole. Quantum entanglement adds another layer of intrigue. When particles become entangled, their fates intertwine no matter how far apart they drift. The ER=EPR proposal takes this further. What if entangled particles are connected by microscopic wormholes threading the fabric of space-time? If true, every black hole we observe might actually be a wormhole's mouth, its other end tethered to some distant point, or even another universe. The entanglement signatures would be nearly identical, save for one ghostly whisper: anomalous heat. Wormholes, unlike black holes, might leak thermal radiation from their far ends, creating faint temperature discrepancies in their accretion disks. Astronomers are now hunting these thermal fingerprints. The black hole at the heart of galaxy M87, already famous for its polarized light, shows puzzling infrared fluctuations that don't align with standard models. Some patches of its disk glow hotter than they should, as if warmed by invisible threads stretching beyond our view. Even more compelling are the quiet quasars' active galactic nuclei that flicker with patterns suggesting their central black holes might be gateways, not endpoints. When matter falls in, it doesn't just vanish, it resonates as if striking a cosmic tuning fork whose vibrations reach places we can't see. Yet the duality goes deeper. If black holes and wormholes are truly two sides of the same coin, it means every singularity we've catalogued might be a portal in waiting. The implications rewrite not just astrophysics but reality itself. Time loops, causality violations, even the universe's holographic nature. all could hinge on this cosmic sleight of hand. For now, the signals remain ambiguous, whispering possibilities just beyond our grasp. But with every anomalous ring down and every too hot accretion disk, the veil between black hole and wormhole grows thinner, teasing us with visions of a universe far more connected than we ever dreamed. At the heart of most galaxies, supermassive black holes roar like cosmic engines, devouring matter and spewing radiation across the universe, but some defy expectations. They're silent. Take a 2261 BCG, a galaxy 3 billion light-years away with a central black hole weighing as much as 1 billion suns. By all rights, it should be a blazing quasar visible across the cosmos. Instead, it's eerily dormant, a sleeping giant surrounded by a galaxy that hasn't just gone quiet. It's missing the very signs that a black hole ever existed there at all. This cosmic silence isn't just unusual, it's borderline impossible. Black holes of this size need to feed. The density of stars and gas near galactic centers should guarantee a steady flow of material spiraling inward. Even if the black hole entered a temporary lull, its gravitational pull would still distort nearby stars, creating detectable velocity shifts. But a 2261 BCG shows none of this. No X-ray glow from superheated gas, no swirling stellar orbits. It's as if the black hole vanished or is hiding in plain sight. Theories attempting to explain this silence fall into two camps: starvation or evolution. The starvation hypothesis suggests these black holes may have exhausted their fuel in an ancient feeding frenzy, devouring all nearby matter and leaving nothing but a gravitational scar. Simulations show this could happen if a black hole's accretion disk fragmented into clumps, falling inward in sporadic bursts rather than a continuous stream. But starvation alone doesn't account for the complete absence of activity. Black holes this massive should still accumulate stray gas over billions of years, creating at least a faint glow. That's where the evolutionary argument takes a radical turn. Some astronomers propose these black holes haven't just gone dormant, they've transitioned into an entirely new phase. Picture a star collapsing into a neutron star, its matter crushed into an ultra-dense state. Could supermassive black holes undergo a similar transformation? One wild theory suggests they might reach a point where their own gravity triggers a phase change in spacetime itself, forming a gravistar, an exotic object with a dark energy core that repels matter rather than consuming it. No accretion disk, no radiation, just a perfect cosmic cloaking device. Yet the strangest clue comes from galactic archaeology. A 2261 BCG isn't alone. Other, coreless galaxies show similar voids where their central black holes should be. Intriguingly, these galaxies also lack the dense star clusters typically found near supermassive black holes, as if something erased both the monster and its footprint. Could these black holes have been ejected during galactic collisions, hurled into intergalactic space by gravitational recoil? Or is there a deeper mystery, a previously unknown black hole life cycle where the most massive simply fade into silence, leaving behind galactic ghosts? The implications rewrite galactic evolution. If supermassive black holes can vanish or transition, it means galaxies might outlive their central giants or harbor invisible remnants that still shape their growth in ways we can't yet detect. And if we're wrong, if these black holes are still there, just hiding, then we're missing an entire chapter in the book of cosmic extremes. Every silent giant is a riddle wrapped in the darkness of deep space, challenging us to rethink what happens when the universe's most powerful engines simply stop. From the rhythmic heartbeat of Jaris 1915 to the phantom echoes of Maxi J1820, these 25 signals have done more than puzzle scientists. They've rewritten the rulebook on black holes. Each one defies expectations in its own way. The WOW signal's unexplained origin, the anti-correlation effect's inverted logic, the orphan jets drifting like cosmic ghosts. These aren't just anomalies, they're cracks in the foundation of our understanding, showing us how much we still don't know. Black holes were supposed to be simple gravitational traps where matter and light vanish forever. Yet here they are, broadcasting twisted light, humming in gravitational waves, even flickering like faulty light bulbs. The deeper we look, the stranger it gets. Are we seeing Hawking radiation's first whispers or something entirely new? Could missing X-ray binaries be cloaked in dark matter, or are they evidence of black holes in hibernation? Every signal is a thread in a larger tapestry, hinting at forces and phenomena beyond our current models. What if Cygnus X1's jets are tapping into dark energy? What if primordial black holes are the key to the Edge's anomaly? The questions pile up faster than the answers, and that's the thrill of it. This isn't just about solving cosmic riddles, it's about the joy of the hunt. Every unexplained signal is an invitation to dig deeper, to question assumptions, and to embrace the chaos of discovery. Maybe one of these mysteries will unlock the next revolution in physics. Or maybe the real revelation is realizing how much wonder is still out there, waiting in the dark. So what's your take? Do you think black holes are hiding even weirder secrets, or are we on the brink of cracking these puzzles? Drop your wildest theories in the comments. After all, the universe's greatest stories are written by the curious, and if you're hungry for more cosmic mysteries, hit subscribe. The cosmos isn't done surprising